This is another classification method which is very popularly used and a promising method for classification of both linear and non-linear type of data. A support vector machine is also known as SVM in short, is an algorithm which works as follows. It uses a non-linear mapping to transform the original training data into a higher dimension. Within this new dimension, it searches for the linear optimal separating hyperplane. We will see what is the meaning of hyperplane, which is a decision boundary separating the tuples of one class from another. With an appropriate nonlinear mapping to a sufficiently high dimension, data from two classes can always be separated by a hyperplane. The SVM finds this hyperplane using support vectors. It's a new concept. We want to understand what you mean by support vectors and what is a hyperplane. Support vectors are essential training tuples and also margins. It is defined by the support vectors. We will see all this. Before going to the details, we will see what are the different advantages of using SVM. Although the training time of even the fastest SVMs can be extremely slow, they are highly accurate owing to their ability to model complex nonlinear decision boundaries. They are much less prone to overfitting than other methods. The support vectors found also provide a compact description of the learned model. This can be used for prediction as well as classification. They have been applied to a number of areas, including handwritten digit recognition, object recognition, speaker identification, as well as benchmark time series prediction tests. So this is having a wide variety or wide range of application areas, and this is a very popular method nowadays. So the relevance of studying SVM is very high. As we have told, SVM support linear and non-linear data. We are checking with the first case, the case when the data are linearly separable. We are seeing simple example, a two-class problem where the classes are linearly separable. Here, the data set can be represented as x1, y1, x2, y2 up to the length of the data set, where xi is the set of training tuples with associated class labels yi. Each yi can take one of the two values, that is either +1 or -1, corresponding to classes bias computer yes and bias computer no respectively. Here you see the figure. Here we have to represent the classes C1 and C2, which belongs to one belongs to bias computer yes and the other belongs to bias computer no. Here we have different training tuples that are separated by using certain lines. Here the 2D training data are linearly separable. There are infinite number of possible separating hyperplanes or decision boundaries. The separating line is called as the hyperplane, or we can say a decision boundary. We can represent infinite number of such hyperplanes, but we have to choose the best one that segregates these both classes. Here in this figure we have represented 6 hyperplanes, and we don't know which hyperplane is the best one. That we have to decide based on the other concepts known as support vectors and margins. Let us see. SVM searches for the hyperplane with the largest margin, that is the maximum marginal hyperplane. We have to choose the hyperplane with the largest margin, that is known as maximum marginal hyperplane, MMH. The associated margin gives the largest separation between classes. Getting to an informal definition of margin, we can say that shortest distance from a hyperplane to one side of its margin is equal to the shortest distance from the hyperplane to the other side of its margin, where the sides of the margin are parallel to the hyperplane. So the shortest distance from a hyperplane to one side, and it should be the largest to the other side. So the classes separating the two, that is yes and no, are two classes here. The hyperplanes that can be represented with the shortest distance from one side and the largest distance to the other side will be the margin. Okay. A separating hyperplane can be written as, using this equation, w into x plus b, that is equal to 0, where w is a weight vector, namely w1, w2, etc. up to wn. N is the number of attributes and b is a scalar, often referred to as a bias value. Okay, so a hyperplane can be written using this particular equation, and b is the bias value, and we can calculate w0 plus w1 x1 plus w2 x2 for each and every attribute values. Here we will see what is the best method for finding the margin or the hyperplane, finding the best separating plane. We will see by example. Generating to n dimensions, we want to find the best hyperplane. We will use the term hyperplane to refer to the decision boundary that we are seeking regardless of the number of input attributes. An SVM approaches this problem by searching for the maximum marginal hyperplane. We have already discussed all these points. We will see the figure as the example. We have a hyperplane here in the first figure, and we have small margin to both the classes, both sides. Okay, and if we can represent a hyperplane like this in the second figure, it provides a large margin to both the classes. Here we see just two possible separating hyperplanes and their associated margins. We have seen only two cases. Which one is better? The one with the larger margin should have a greater generalization accuracy. So we choose the second one with the large margin. The weights can be adjusted so that the hyperplanes defining the sides of the margin can be written as hyperplane 1 can be written as w0 plus w1x1 plus w2x2 will be greater than or equal to 1 for the class 1, and h2, that is the hyperplane for the other class, can also be represented using the same equation, which will be less than or equal to -1. That is, any tuple that falls on or above h1 belongs to class +1, and any tuple that falls on or below h2 belongs to class -1. Combining the two inequalities of equations mentioned above, we get a common equation like this. This can be used to represent the hyperplane. Any training tuples that fall on hyperplanes h1 or h2, that is the sides defining the margin, satisfy equation above and are called support vectors. So what do you mean by support vector? Any training tuples that fall on hyperplanes h1 or h2 satisfy equation above are called support vectors. So which is closer to the hyperplane, that the training tuples can be referred as support vectors. That is, they are equally close to the separating maximum marginal hyperplane value, that is MMH. So that tuples are referred as support vectors. Thus, any point that lies above the separating hyperplane satisfies the first equation w0 plus w1 x1 plus w2 x2 greater than 0. Similarly, any point that lies below the separating hyperplane satisfies W0 plus W1x1 plus W2x2 minus 0 is known as the support vector. For example, here the tuples represented very near, or the tuples lies on the MMH, that are referred to as support vectors. Okay, support vectors are represented in this particular figure. The SVM finds the maximum separating hyperplane with the help of support vectors. And we have to see the other case, the case when the data are linearly inseparable. Some cases we can't separate the data linearly. This is an example for such cases. In such cases, no straight line can be found that would separate the classes. The linear SVMs we studied would not be able to find a feasible solution here. What we can do, the approach for linear SVMs can be extended to create nonlinear SVMs for the classification of linearly inseparable data. These are also called nonlinearly separable data, or nonlinear data for short. Okay, so we can see the case of nonlinear data. Such SVMs are capable of finding nonlinear decision boundaries, that is, nonlinear hypersurfaces in input space. This is an example for such case. Here we can't linearly separate the two classes with a hyperplane, with a single hyperplane. So what can we do with this type of examples? Or we can use we can handle nonlinear data by using SVM. We have to. There are mainly two steps can be used. First step, we can transform the original input data into a higher dimensional space using a non-linear mapping. So we can transform the data into a higher dimensional space using non-linear mapping. Several common non-linear mappings can be used in this step. And in step 2, once the data have been transformed into the new higher space, the second step searches for a linear separating hyperplane in the new space, as we have discussed with the first case. So first step, we have to transform it into a higher dimensional space with using a nonlinear mapping methods, and then we can do for the same method we have discussed earlier. Aside from classification, SVMs can also be designed for linear and non-linear regression.